Now we will do example 14.1. We are asked, it's on page 421. So we are asked to use the bond energies to determine the delta H of the following reaction. So we have 2H2 plus O2 yields 2 moles of water. All right, so this is a composition reaction, but we need to use the bond energies that we were given on the table on page 420, but we don't know what bonds we're working with. So we've got to go back and use our Lewis structures that we learned earlier on in the book. And if you need refreshed on that, you can go back in the book and look at the Lewis structures. But so what we need to do is write out the Lewis structure of this reaction to be able to tell what bond energies we're working with. All right, so first of all, I want you to remember that on the table on page 420, the bond energies are the energy required to break 1 mole of a given type of bond. All right, we're not always just breaking 1 mole. As you can see here, we actually have 2 moles of the HH bonds. And so we have to take that into account when we're calculating the overall enthalpy change. So when we draw this out, we have our HH bonds, right? Oh, and before I go on, this equation is already balanced, so you don't have to work on balancing equations. They will be balanced for you. You just have to be able to write the Lewis structures for these molecules. So we have the HH bond. Well, we have 2 of them, all right? So we've got 2 HH bonds, all right? And then we have our oxygen. And if you'll remember from our Lewis structures from before, that the O2 molecule actually has a double bond between the oxygens. So we are going to have to break a double bond there. And then we are yielding our H2Os, but we have 2 of them. And so we're going to draw 2 H2Os. And we actually will draw them like the regular H2O that we know. All right. Plus OH. All right. So what we're looking at now, we have to find the bond energy for every bond here, which means we've got to account for this bond, and this bond, and this bond, and this one, this one, this one, this one. All right, if you look at these ones, all of these are HO bonds, okay? They're HO or OH. It doesn't matter what order you give these, what order the bonds are even written in on the table. If it's HO or OH, it's the same thing. It requires the same energy. So if you remember, our delta H is our energy for breaking bonds, okay, minus our energy for making bonds. All right, so we're going to take our bond energies here, which we're breaking these bonds, and we're going to add all of these up for all of the breaking bonds, and then we subtract all of the making bonds. All right, so we look in our table, and an HH bond is 436 kilojoules per mole. But remember, we have 2 of them. So we say 2 moles times 436, I got this out of the table on page 420, kilojoules per mole. All right, our moles cancel out. Okay, and over here, now we only have 1 mole of the O2, but we've got to cancel out the moles because the units have to be the same in both of them. So even though it's times 1 mole, you still need to multiply it by 1 mole so your moles can cancel out. I'm sorry, this isn't 436. Breaking the OO bond, the double oxygen double bond, is 498 kilojoules per mole. All right. The moles, again, cancel out, and we're left with kilojoules. But this is all of our breaking bonds, right? We took care of the 2 hydrogen bonds, and we took care of the double bond in oxygen. That's all of our breaking bonds. Now we subtract our making bonds. We could do this as 4 separate things, but since these are all the same, we're just going to say 4 moles, right? Because we have 4 of these bonds to break. And it is times, and these are HO bonds, which are 460 kilojoules per mole. And again, our moles cancel out. So we're left with kilojoules, right? We have kilojoules, kilojoules, kilojoules. So now we do our calculations. And once we type all these into the calculator, so it's 2 times 436 plus another 498, and we subtract 4 times 460, and we get minus 470 kilojoules. Okay, that's our answer. Plug that into your calculator. If you do not get that, practice working your calculator again. These are the numbers that you need to type in. Now, with the answer being negative, that means delta H is negative. What that means is that it is possibly a spontaneous reaction. We will talk about one other thing that goes into explaining that later on in the book, but we have a negative delta H. Okay? And remember our significant figures, all right? So remember, when we're doing these, when we're adding things, the way we get our significant figures is we go with the least precise significant number, all right? So this one goes to the ones place, this one goes to the ones place, this one only goes to the tens place. So that's why our answer only goes significant up to the tens place, all right? So remember that. That is a significant figure rule that we are seeing time and time again. And I will end this video and I will start another one for the next calculation.